Morning. All right, so today for Chem 103, we're going to go through the calculations for the biodiesel project. So now you should all have your data at this point, and we're going to take a look at what types of things you need to do to actually make all of that data meaningful. The GCMS data, we're going to go through that today also. I don't have the latest data uploaded yet. I haven't gotten it from Harper yet, but as soon as I get that uploaded, then you'll have that, and today we'll look at somebody else's, some old data, just so you get a sense of what that's going to look like and what we do with it. Just a reminder, for this week, the stuff is the only things you need to turn in relation to this project are your notebook data pages from the lab and these calculations that we're going to do right now. Normally that stuff's all due tomorrow night. If you can't get it done before the weekend, that's fine. The weekend's meant to be kind of a open period where you don't have to do everything as long as you got stuff done. But if you need that extra time, you can turn it in there as well. All right. So before we get into the calculations here, let's take a look at Blackboard just to kind of see some of the references that you're going to need. So this is the biodiesel project folder. And you've seen the first couple of these with the instructions. The final analysis here, this is what you're going to end up answering as your project. That to load here a second. Here we go. So today we're going to focus on, so number one here, did you produce biodiesel? That's kind of like the taking everything that we did, all the tests, and putting it all together to prove if your stuff is actually biodiesel or not. Today, we're going to focus on the calculations, which are 2, 3, 7, and 8. So 2, 3, 7, and 8 are calculations, and we will be doing those. So I think the first ones I have up are heat of combustion from the bomb calorimeters. So we'll start with that. That's number 7. This document, hold on, let me change this. The document I was looking at, this one, is available on Blackboard, so you can follow along with the calculations, and I'm going to just kind of walk you through it here. So, as we talked about last time, the heat of combustion is calculated by looking at the amount of water that the calorimeter was in and the change in temperature. Now, because of some other things going on, we have to do a couple different heats. So, up here you see Q. Q means heat. And the general formula for heat is the mass of the water times the change in temperature times the heat capacity, which is how much energy does it take to change the temperature of a certain material. Now for water, that's 1, so we don't have to worry about that. But in our case, for this experiment, we didn't only heat up the water. We heated up the water, and we also heated up the calorimeter, that big chunk of steel. Takes some energy to get heated up as well. So we have to account for that. And then also we need to subtract the heat that was produced by the wire, because the burning wire gave off some heat that is not from the biodiesel, it's from the wire. So we subtract that heat. All right, so we'll kind of take these one at a time so you can see how to calculate them. And if you're watching along live, you can ask questions in the chat or on Discord, and I'll address your questions there. So we'll start with the first term here, the heat from the water. This is the one that we've talked about before, and it's simply the mass of water times the change in temperature. So you all should have used 4,000 grams for each trial. So the mass of water is always going to be 4,000. We can ignore the heat capacity term here because it's just 1. And the delta T is the change in temperature. So let's say, let me do an example here. Let's say you started, or your final highest temperature was 25.9 degrees C, and your initial temperature was 25.0 degrees C. So you would subtract those two numbers, and then your delta T, or your change in temperature, is 0.9 degrees C. And so that's what you'd multiply by the mass of the water, and that is how much heat went into the water, because the heat from the biodiesel went into the water to change that temperature. So that's your first term. Okay. Now the heat capacity of the calorimeter, that's not something that we measured directly in lab. That's something that we have to basically do the opposite. We have to take something that we know the heat how much heat it produces, and we put it in the calorimeter and we measure the temperature change, and we use that to calibrate the calorimeter. So the numbers for those are actually in Blackboard. Let me show you where you can find them. They're also in the Biodiesel project folder. And they're down here on heat capacities. There's a couple different versions. Use the newer one here. I think we may get an even newer one, but we have to wait for another class to finish that. So I don't know that we'll get that in time for the calculations this year. But the heat capacities of the calorimeters don't change too much over time. So this is where, let me see if I can bring this up on the screen. Oh, there it is. Okay. So it's just an Excel file of these heat capacities. And so you have to look up which number heat calorimeter you had. That was that 3-digit number on the black sticker up at the top there. And then use these bottom averages for your heat capacity of the calorimeter. So let's say we had this first one, number 469. We're going to use 1435. So if we go back to our calculations, that would be this number right here, the heat capacity of the calorimeter. That's what you're getting from that table, and the change of temperature. Now, if you're the group that use the new ones that we that aren't going to be on that table because we just got them, I don't know if we're going to get the actual numbers from that before you need them. So you can just pick one. They're all fairly similar. So just pick one of the ones on the table for now, unless I can get those in like today. All right, hopefully that's making some sense so far. And then for the last term that you're going to subtract here, you're going to take the length of the wire that you used and multiply by 2.3, because every centimeter of wire gives 2.3 calories. And then, or if you weighed it, multiply the mass in grams by 1200. I think everybody used the centimeters, if I'm not mistaken. So, all right, so this should give you 3 different numbers: the heat from the water, the heat from the calorimeter, the heat from the wire. You're going to add the first two, the water and the calorimeter, and subtract the last one, that heat from the wire, which should be a pretty small number. And that's your total heat, and that's in the unit of calories. So in little c calories, that's how much heat was produced by your biodiesel for that particular trial. Let's say trial 1. Okay, so that's a starting number. The problem with that is you're going to get a different number for different samples, different amounts of biodiesel. And even though the directions said use about 0.5 grams, most people didn't use exactly 0.500 grams every time. You didn't have to. So what we want to do is kind of standardize this. So we're going to use a concept called energy density. Instead of just the raw energy, the calories that came out, we want to know how many calories per gram of biodiesel burned. So to calculate that, you're going to take the calories from above, what you just, that big number that you just calculated. And just to give you a sense, everybody's going to be a little bit different, but it should be right on or somewhere around 9,000 calories, I think, is what we generally get. Maybe 7,000, 7 to 9,000, something like that. If you're in that general range, you're probably fine. If you're getting like 700, that's not right. If you're getting 7 million, that's not right. Let me know if you're having trouble with that. So your energy density is your calories that you just calculated divided by the grams of the biodiesel that you burned in that particular trial. So calories divided by the grams of biodiesel. Since it's about 0.5, that should get you to... Yeah, no, I think that number's wrong. I think most people are getting in the 13 to 14,000 range for calories up here. This number, this total calories, and then grams you got about half a gram, so you're going to end up. Well, here are some basic numbers. If you have a question, let me know. I don't have those numbers with me. If we say that this is a reasonable number, then the energy density probably should be around 7,000 calories per gram. Again, if you're not way off that, you're probably fine. Even if you are, you may also be fine, but you can always check with me. Okay, so that's done. That finishes up our number. Well, it almost finishes, I guess, our number 7. The energy density that we calculate here is going to be in calories per gram. That's the unit, calories per gram. But when we want to compare this to other fuels and look up other data, fuel tables, things like that, on the fuel table and things like that, so we can compare to gasoline, other types of fuels, we need it in a different unit, BTUs per pound. BTU stands for British thermal units. It's an older unit of energy measure that we still use in the US. So to calculate or to convert from BTUs per pound, you're going to take your calories per gram, divide by 252, and multiply by 454. If you're not clear, if you're not comfortable with these types of unit conversions, if you haven't really done that before, that's okay. But just follow along. So you're taking your calories per gram divided by 252 times 454, and that gives you your answer in BTUs per pound. And so that way you can compare to the known data. And so the known data is going to be on a table, again, in the biodiesel folder, which is not. Okay, there it goes. That is right up here, fuel table. So this is a big PDF of all kinds of data for different types of fuels. You got gasoline, diesel fuel, methanol, ethanol, methyl tert-butyl ether, propane, natural gas, hydrogen, and biodiesel. The biodiesel all the way on the right is like commercially produced biodiesel. So we want to compare to the heating value, which you can see here is in BTUs per pound. There is a, oh, hold on, you can't actually see that. Well, anyway, you know what, maybe I can move. Okay, there we go. So you can see over on the right or the left here, there's heating value, and there's 4 different rows. There's lower and higher, and they're both represented in BTUs per gallon and BTUs per pound. So we want BTUs per pound. I'm not going to tell you whether to use the lower or higher. You have to figure that out based on the definitions. That's one of the questions. So when you figure that out, you go over here to the right there, and you're going to pick your value, and that's what you're comparing to. So let's just say, just for an example, that value is around 17,000, because the higher and lower are both around 17,000. Your percent recovery is going to be your value divided by this accepted value. Don't use 17,000 even, use the correct value from the table, but that's going to be the accepted value, and then you're going to multiply that by 100%. So that just tells you like how did your number compare to the reported value for commercial biodiesel. And in this case, it could be over 100%. You could be getting more heat out of your biodiesel than the commercial sample, or it could be less. We just want to know like in what's the range there? How close is it to the known value? All right, so that takes care of questions 7 and 8 on the report here. You can see that here. So next we're going to move up to 2 and 3. And 2 and 3 deal with calculating yield. How much biodiesel did you get based on how much oil you started with? So if we go down to the next page of our calculations here, you're going to need your starting mass of oil. Yeah, I'll try to get out of the way here. Your starting mass of oil and your final mass of biodiesel. The starting mass of oil is the mass that you started with weeks ago, so you'll have to look back in your notebook and find that number. It should be somewhere around these numbers here, so it should be in the high 80s, low 90s, something like that. If you have some number that's much bigger, chances are you didn't subtract your glassware mass out of that. So look around, like, if you had an empty graduated cylinder and then you've got the mass of the cylinder or the flask. I don't remember. I think we measured it in a flask. So you weighed the flask empty, you poured the oil in, and then you weighed it full. So then you have to subtract the mass of the empty flask. And then the same thing with the biodiesel, which we did either yesterday or last week. You weighed an empty flask or beaker, you emptied the biodiesel into it, and then you reweighed it. So you got to subtract out the empty one again and get the actual final mass of biodiesel. Depending on your washing steps and a bunch of other factors, that mass could kind of be all over the place. So it shouldn't be more probably than what you started with, but it could be quite a bit less. All right, so to calculate these yields and such, it's a fairly complicated process where we can't just use the mass of the starting and the mass of the ending, because in a chemical reaction, the chemicals actually change their masses as they rearrange atoms. So we have to instead have this process here where we convert to moles and then use the molar ratio from the equation and so forth. If any of you are interested in going through that in more detail, I'd be happy to show you, but it's not something that it's a little beyond what we're trying to do in this class. So if you just follow through the calculations, basically you're going to use your starting mass of oil from weeks ago in there. And then all the other numbers, you're going to use my numbers here. So you're going to divide by 880, which is an approximate molar mass of the oil. You're going to multiply by 3, and you're going to multiply by 295, and you should get something like this, which is called the theoretical yield. And the reason that's theoretical is what that number represents is if every single bit of your oil was transformed into biodiesel, the reaction worked absolutely perfectly, that's how much you'd expect to get. And that's a theoretical number because every chemical reaction, there are various factors at play that affect that. So you can almost never have every single molecule converting to the product and being recovered. You almost always have to get less for various reasons. It's not just about making mistakes or being careful, it's just about how the chemistry works. So that's why this one's theoretical. So then what we do is once you find that theoretical yield, you're going to plug that into this next equation where you take your actual final mass, what you measured yesterday or last week, and divide by this theoretical yield that you just calculated and express that as a percentage, and it tells you what is your yield of this process. So 89.5% yield might be a decent yield for this reaction. If you're doing this on large scale, let's say you're making tons and tons and tons and tons of biodiesel in a massive factory, every 0.1% yield that you can get translates to a lot of fuel. So a lot of chemical engineering and processes and things go to how do we maximize that yield and get as much biodiesel as we can from a given starting sample. All right, so that's those calculations, and that should take you through what you need to do for this week. Next week, we're going to talk more about some of the details of the project. But the last thing I want to do today is talk about the GCMS because I'll be posting those results today as soon as I can get them. So if we go back to the folder, I just kind of leave all the old stuff from previous years in here so that we have some examples to look at. If we open up this GCMS folder, we'll see some data from a couple years ago. And it's going to look something like this. So what we're looking at here hold on, you can't quite bottom yet. All right, so what we're looking at here is a graph, and the x-axis represents time, and the y-axis just represents amount, basically, intensity. If you remember back when we did the calorimetry experiment, you put the inks on the paper and then ran the liquid, and the different colors went up the paper different amounts. So they took different amounts of time to reach the end. Gas chromatography is basically the same idea, except this time we injected your sample into a small tube and then pushed it with gas, and then certain molecules spend longer going through that tube than others. And so that's how we can separate things in a gas chromatography machine. Then when they get to the end of the tube, they get weighed by a special instrument called a mass spectrometer, which can kind of weigh individual molecules and give you a sense of what those molecules are. So in this example from a previous class, what we're seeing is these peaks are where the molecules came out, and how big the peak is, like how much area is under it, corresponds to how much of that particular molecule is there. So what this one's showing you is just after 10 minutes, something came out. And then just after 11 minutes, something much bigger came out. You can see this much wider, taller peak. So that's going to be like the thing that's the most in our sample probably. And then a little while later, some other stuff came out. And so each one of these peaks represents some molecule that got separated from the other molecules in this machine and then came out the back. And that's all we really get from this. What's more useful for our purposes is the results of that mass spectrometry. So as those peaks come out, they go through this other instrument, and that instrument is able to, with the help of some software, identify what that molecule is, or at least try to. So each of your files has 2 pages. The first one is that chromatogram that I just showed. That's the graph. And then the second page is this report. And so let's talk about what's going on in this report. So you've got a few columns here. A peak number, RT, which stands for retention time. That's the time that peak happened on the graph. How much of the sample is this area by percentage? And then what the software thinks it is. Some other numbers about that. And then the last one you have to worry about is this very last number, qual, which tells you how good of a match is it. So like how confident can we be that that's actually what this thing is. So let's do this for example. So we'll take the first peak. The first peak has an RT of 10.43. So if we go back up to the graph, we can find 10.43 is right here. So we're talking about this thing here. We can also see here that it was about 8% of the overall mixture. And the software thinks that it is hexadecanoic acid methyl ester. And it's about 98% sure. It's also giving you these other choices with a little bit lower certainty because sometimes it can't quite tell, or it just wants to give you some other possible choices. But that looks pretty good to me. So probably that first peak is hexadecanoic acid methyl ester. Now, what is that? Well, who knows? Well, I mean, we can look it up. Let's say it that way. So I'm going to look up hexadecanoic acid methyl ester. Okay, which is also known as methyl palmitate. And if we're just kind of reading the stuff here that comes up, this occurs naturally in crude palm oil and walnut. It is one of the famed components of biodiesel fuel produced by the transesterification of triglyceride oil and a primary alcohol. And right, that's exactly what we're looking for. FAME, fatty acid methyl esters. So we can confirm now that thing, whatever that molecule that came out, is a fatty acid methyl ester and is part of the biodiesel. So great. Now the largest component of our mixture is peak number 2 here. It's got 83% of the area. That's the biggest thing. And so that one's saying that it's either 9-octadecanoic acid or 10-octadecanoic acid, 11. It can't separate those in the machine. So it's one of these things. But the good news is those are all fatty acid methyl esters. Again, you can look them up and you'll find that those are also fatty acid methyl esters. So there's even some help with this in Blackboard, because right in that folder, that GCMS folder, it says when you get these hexadecanoic acids, those are palmitic octadecanoic acid. Octadecanoic acid is oleic acid. We expect that to be a big component of oils. So all that stuff is in there, and that's good evidence that we did indeed make biodiesel, because the major things that are coming out are what we want them to be. They're biodiesel molecules. So that's how you use the GCMS data. And as I said, your data will be coming up as soon as I can get it posted to Blackboard, get it from Harper. So hopefully that gets you going with the biodiesel project and as everything you need for that. If you have any other questions, of course, let me know. And happy calculating. The project itself will be due in the next module, so in a little over 2 weeks. All right. Also, if I know we had some issues with the cleared for Harper thing, so make sure that if you are doing the testing that you get that in before noon on Thursday every single week. Even if you're not coming to campus a particular week, you still have to get tested and put it in. Otherwise, you get a couple warnings, and I don't know what the eventual consequences are, but I don't think they're good. So make sure that you're doing that every single week. If you've gotten your vaccine cards in, you don't have to worry about it. You're good for the rest of the semester. All right, thanks everybody, and I'll see you next week.